All right, let's do this. This is 3.5. I didn't pull it over, sorry. So 3.5 is kind of long. Multiplying complex conjugates. Okay, so if I have a polynomial, more specifically a quadratic, and it misses the x-axis, does that have any roots? It doesn't have any real roots, but the fundamental theorem of algebra says every polynomial of degree 2, every quadratic equation has 2 roots. Every cubic equation has 3 roots. Every x to the 4th equation has 4 roots. So how can this have 2 roots if it misses the x-axis? The roots are imaginary. And they always come in pairs. So something like this. 3 plus or minus 4i. Okay. Now, what do those roots mean? That's a little bit difficult. But one cool thing is, if you get rid of the I, and you do 3 plus 4 is 7, and 3 minus 4 is negative 1, if you flip this upside down, I missed, but so if this is my parabola, if you flip it upside down, it hits at negative 1 and at 7. That's kind of interesting. Okay, but complex roots always come in pairs every single time. So it's always 3 plus or minus 4i, or plus or minus 6i. You can't have 2 plus I and 7 minus I, right? That doesn't ever happen. They're always in a pair, and the pairs are always conjugates, meaning they're exactly the same, but the sign between them is different. So this is called a complex conjugate. So what does that equation, what is the equation for this situation? Well, if I had x equals 4 and x equals 3, how would I create a quadratic? You would say x minus 4 times x minus 3, and then multiply it together. Well, the exact same thing happens here. So we're going to subtract the 3, so x minus 3, and then we're going to subtract the 4i, right? And what's the other one going to be? X minus 3 plus 4i. And then we multiply those together, and that will give us our equation. Now, look at this. So we need to distribute this negative before we multiply, right? So x minus 3 minus 4i times x minus 3 plus 4i. Okay, now one more thing before we multiply that together. If I had x minus 9 times x plus 9, something interesting happens. When I multiply that out, I get x squared plus 9i minus 9i minus 81, and those cancel. And that gives me x squared minus 81. What do we call this? Difference of perfect squares, right? And these are conjugates. Anytime you multiply conjugates together, this stuff is going to cancel out. Remember that. Okay, let's multiply this. X squared minus 3x plus 4xi. So the order is number, variable, I, and then if there's a square root, it goes after that. So the order that we write our terms, number, variable, I, roots. Okay. All right, then we move on to the second one. Minus 3x plus 9 minus 12i. Does everybody follow? Okay, now this one, minus 4xi, this one, plus 12i, good job, and this one, minus 16i squared. Ah, good. We'll talk about that. Now take a look at this. 4xi is opposite negative 4xi. Okay? And negative 12i cancels 12i. And what about these? Do they cancel? No, they're exactly the same. So we're left with x squared minus 6x. And then what is I squared? Negative 1. Because I is the square root of negative 1. So I squared would just be negative 1. So this turns into plus 16, and that combines with the 9 to give me 25. And what do you notice? There are no i's. They all canceled. Why did they all cancel? Because these are conjugates. And that's why complex roots have to come in conjugates. Because our quadratic equations can only be written using real numbers. So the only way to have a quadratic miss the x-axis and contain only real numbers is to have roots that are complex and conjugates. So the cool thing about this is this cancellation will happen every single time. And this cancellation will happen every single time. So we can just skip them. If you know they're going to cancel, you don't even need to bother writing them down. So say I had x plus 1 minus 3i. What would the other one be? Nope, it's got to be. So this would be negative 1 plus or minus 3i plus 1 plus 3i. When I'm finished multiplying these together, there will be no i's. So we'll skip a lot of them. Do I need this? Yes, x squared. Do I need this? Yes, in fact, I'm going to have 2 of those, right? So this one is x times 1, and this one is 1 times x, which gives me 2x. Okay? Do I need that one? No, because it's going to have an opposite somewhere along the way. Okay? I already did this. Do I need this? Yes. So I'm going to write that over here, plus 1. Do I need this? No, that cancels the one that we skipped before. Okay? Do we need this? No. Do we need this? No. Do I need this? Yes, and what will it equal? So negative 3i times 3i is negative 9i squared, which becomes 9. That is my quadratic equation. So go ahead and multiply all of them if you want, but we can skip every I except the I squared. Because I know that the single i's are going to cancel, and then the I squared is going to become negative 1. So that quadratic right there misses the x-axis, and its roots are negative 1 plus 3i and negative 1 minus 3i. All right. So here's a bad thing about complex numbers. You have to get really far into mathematics before you see a practical use that helps you. Anyway, they are used to build functions. So if you have, let's say you're modeling something Like you have a bunch of dots, and you need to build an equation that models that. Well, this represents a set of imaginary roots, and this represents a set of imaginary roots. So you would have to build a function that had imaginary roots. So, but they're used all over the place. They're used in electronics. They're used lots of modeling. They're used in trig, all sorts of trig stuff, but nothing that's going to make a lot of sense today. So, sorry. Okay. All right. So I need a polynomial for this. What is the factor for negative 5? X plus 5. What is the factor for 8? Minus 8, x minus 7, x, and x minus 1. That's pretty easy, right? What if I had 3/4? You could say x minus 3/4, but nobody does. How else would you do it? So if I had x equals 3/4, how could I build a factor that didn't have a fraction in it? You could do decimal, okay? Or what factor equals 0? What could I put here and here to create 3/4? It would be 4x minus 3. Right? Okay. All right. So, how is a single root represented in an equation? What would that root be right there? What would this look like? X plus 3. Okay. What about a double root at, or sorry, I just gave it away. What about a bounce at negative 2? That would be x plus 2 squared. Right? Okay. What about this? So how is a saddle represented? That's an x cubed. So that saddle right there would be x to the third. X plus 0 to the third. So let's do a couple of these. All right. So I have at negative 3, I have a single root. So x plus 3. Right? What happens at 2? It's a double root because it bounces. So x minus 2 squared. Okay. Now, is this graph going up or is it going down? Down, which means I need to put a negative out front. You see that? Okay, let's go on to the next one. So x minus plus 3, x minus 2 squared. Is this going up or is it going down? It's going up, so it gets a plus out front. Okay. All right. So x plus 3, x minus 2, and x minus 4. Positive or negative out front? Positive. Is everybody all right with that? Let's do the next one. Okay. So this is x plus 2 to the first, and then that's a triple root. So we could write x minus 0, but we don't need to. We just write x. And then how do we represent a saddle? Is that a positive graph or a negative graph? That's a negative graph. So we sort of have two different options. This is a positive graph, and this is a negative graph. So it might, it could do something in between. Or this is a positive graph, and this is a negative graph. What's the difference between these and these? When do the ends go in opposite directions, and when do the ends go in the same direction? What? Yes. So these would be x to the thirds, x to the fifths, x to the sevenths, and these would be x squareds, fourths, and sixths. So if the number of x's is even, then the endpoints are going to go in the same direction. Up, up is positive, and down, down is negative. If the number of x's is odd, then up to the right, down to the left is positive, and up to the left and down to the right is negative. Okay? So this looks like an x to the fourth. So this is x plus 2 squared, and this is x squared. And do I put a positive or a negative out front? Positive. So that is called end behavior. All right? All right. Find all x-intercepts and the y-intercept. The y-intercept is super easy. We just plug in x equals 0. So 0, 0, 0. My y-intercept is 0. Okay? How do we find the x-intercepts? Well, we need to factor. Okay? What do these all share? 2x. So I pull out a 2x, and I'm left with x squared plus x minus 12. So 2x, x plus 4, and x minus 3. So what are my x-intercepts? 0, negative 4, and 3. You good there? So what would this graph look like? So it's going to look like this. It hits at 3, at 0, negative 3, 0, and at 4. So you would just type in 0, comma, negative 4, comma, 3. Yeah, you need all three of them. Okay. Let's see if these get any harder. Ooh. All right. Here we have an x to the third with 4 terms. The only way you know how to graph that is by grouping. So let's group those and group those. What do the first two share? X squared, and I'm left with x minus 1. What do the second two share? A 9. So plus 9, and I get negative x plus 1. Do those match? Almost. So instead of pulling out a 9, I'm going to pull out a negative 9, which is a little tricky, but what does that give me over here? X minus 1. Okay. What do this and this have in common? X minus 1. So I yank out the x minus 1s. So x minus 1, and what's left? X squared minus 9, and that factors more into x minus 3 and x plus 3. So what are my roots? 3, negative 3, and 1. What is my y-intercept? You just plug in 0, 0, 0, 0, 9. So what does this graph look like? Well, it hits -3, 3, and 1, and it hits 9 up here. So -3, 1, and 3. That's what the graph looks like. All right, let's look. They might throw in one more type. No, probably not. Okay, that's back to the original. Okay. All right. What are the roots here? X equals 0 from this one. What else? -13 and 8. How many times does 0 happen? The multiplicity is 2. What does multiplicity 2 look like on a graph? It's a bounce. Okay. How many times does -13 happen? 3 times. What does that look like on a graph? Saddle. And how many times does 8 happen? 3. So that's also a saddle. So how many of our roots have a multiplicity of 1? None of them. So don't write 0. None. Right? How many have a multiplicity of 2? 1, just the 0. And then both -13 and 8 have multiplicity 3. All right, that'll be good for today. So just do the first, what was that, 5 questions? I think there are 9, so maybe you have some of them already. Oh, 4 minutes in class. All right, get started. We'll finish this on next week.